Okay, Assalamualaikum and good afternoon. We will look into the next chapter, chapter number 2, for the kinematics of particles. And here we look into the force and acceleration. Okay, we start with section 2.1, Newton's second law of motion. For the introduction, as you all know that summation of forces is equal to the mass times the acceleration. And from the Newton's second law of motion, if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in the direction of the resultant. It must be expressed with either a Newtonian frame of reference and one that is not accelerating or rotating. This form of equation is for a constant mass system. Okay, for the linear momentum of a particle, we can replace the acceleration by the derivative of the velocity, like so. Okay, on our right here, we can see the black line is the path of this particle of mass m, and move at a velocity of v. So we have a momentum of m times v mv. So now, summation of forces, you can see that it is a mass multiplied by the rate change of the velocity, or it is a acceleration. And we can further simplify this into this expression, dl over dt, or the linear momentum of the particle. Okay. Linear momentum conservation principle states that if the resultant force on a particle is zero, the linear momentum of the particle remain constant in both magnitude and direction. Okay. There are four primary dimensions, which is the forces, mass, length, and time. Here we can see that there is a mass of 1 kg moved to the right, and we can assume that it is moving at 1 meter per second, and therefore we have the total force of 1 Newton, because 1 times 1, so equal to 1. The same way here, if we have mass of 1 kg drop from certain height, and we know that the acceleration of gravity is 9.81 meter per second square, and therefore the weight of this particular block is 9.81 Newton. Okay. Typically or commonly, usually we are using this international system or SI units, and the units for the length is m, length, mass is kg, time is second, and the unit for the force is derived as so, and is commonly referred as a Newton, which is also equal to kg meter per second square. However, in some countries like US, they use their own units, customary units, and then they will use like pound or foot pound, okay, slug, or something like that. Okay, and the unit for this gravity acceleration, if you use that particular US unit, the acceleration is 32.2 feet per second square for the gravity. And if it is the forces. Okay, Newton's second law. Although this is the general expression, a general formula, but then you can also represent it in the I, J, and K with their respective magnitude. Okay, Fx, Fy, and Fz. direction, and further expand as MAXI, AYJ, AZK, and for example, this one, summation of fx, this part here, okay, this, okay. So on this part, fx, so we have this max, and therefore we write it over here. Then we have fy and ayj, of course with m, so we have this, okay, and also for this and this one, we have this part, okay, and we know that uh, okay, uh, originally we have x for the distance, then we took the derivative of this, we get x dot or v for the velocity. Then we have also the 2x over dt, which is equal to dx dot over dt, which is equal to x double dot, or equal also to a, this is vx, ax. Okay, so this one here is this, okay, in the x. Like so, you can do for the y and z. Okay, moving to the next slide. Okay, now, from the second law, suppose you see something like this, right? Summation of forces F minus MA equal to 0. So means that there is some motion involved. Okay. Okay. Now, with the inclusion of the initial vector, the system of forces acting on the particle is equivalent to 0. The particle is in dynamic equilibrium. Methods developed for particle in static equilibrium may be applied. Coplanar forces may be represented with a closed vector polygon. Okay. Initial vector are often called the initial forces. The measure the resistance that particle offer to change in motion. To be specific, it is the changes in speed and also the direction. Okay. Initial force may be conceptually useful, but are not like the contact and gravitational force found in static. Okay, moving on to the free body diagram and kinetic diagram. What we have here is we have a block weighing 15 kg. It is placed on a slanting surface with an angle of 25 degree, okay, block B. Then here is the right triangle here is the block A, and then attached to this particular line or rope, and this particular line or rope is being pulled by 225 Newton of force to the left. Okay. Now, the free body diagram is the same as you have done in static. Okay, we will add the kinetic diagram in our dynamic analysis, like what we have here on this part. Okay. Okay, to simplify this particular problem, okay, to make your life much more uh, to make it more easier to be analyzed, then we define our coordinate system or our reference frame is like so, like this one. X pointing to the upwards left, and Y is to the a bit to the right and going upward as well. Okay, so this is our reference axis. Okay, now we know that it is slanting at the angle of 25 degrees. Okay, it is here, and we since this particular block will have a weight, okay, which is equal to mg, like this one, g. This is our weight. Then this particular angle here is theta, which is equal to this one. This is our theta, 25 degree. And this line here is basically 90 degree to this particular surface. Okay, and it is of course pointing upward because it is a normal forces. And this one here is the forces that's due to this part. Okay, we cut this particular line here. Okay, so this is our forces, line of action, the direction. Okay, this is the step that you might you can use. The first one, you isolate the body of interest, free body. Okay, just this part and at a certain angle, then draw your axis system. This one, this is your axis system. Okay, add in applied forces, where applied forces is this one. This is your applied forces, 225. And then replace support with forces, like the normal forces, like so. It is your support forces. And then, of course, your weight of that particular object. And then draw appropriate dimension, usually angles for the this part. Okay, that is the a general steps on how to do that. Okay, put the initial terms for the body of interest in the kinetics diagram. Okay, the same procedure. Okay, and you can also represent it like so, like this one. So you will have a basically you when you want to resolve this particular problem, we will look into the summation of forces in the x and also in the y axis. Okay, we go on to this example. Okay, we have 80 kg block rests on a horizontal plane. Okay, find the magnitude of force P. Okay, P, how much P is required to give the block an acceleration of 2.5 meter per second to the right. So we want this particular block to move here with an acceleration of 2.5 meter per second square. So we want this to move to the right with this speed, acceleration. Sorry. The coefficient of kinetic friction between the block and plane is 0.25. Okay. Here, because this block is sitting on this horizontal plane, and therefore will have a contact, and that particular contact will have a certain friction. Okay, and that particular friction is mu k is given 0.25. Okay, and this item is going to the right, and therefore we know that friction will always in the reverse direction of the forces. So it is your friction force, FF. Normally I use this term, which is equal to mu K times the N. We will look into that much clear later. Okay. First, we draw our free body diagram together with this axis. If you don't have this part, it will be difficult for you to analyze this problem, and also will give a lot of problem for me to see on how you approach this particular problem. Okay, first we look into the forces in the x-axis. Okay, okay, for static, when you learn static, okay, what happen is you will have summation of forces is equal to 0. However, for the dynamics, the summation of forces is not equal to 0. It will have certain value. Okay. For dynamic, remember, it will not equal to 0 because dynamic means something that is moving. Yeah? Okay, first we resolve into the forces in the x direction, F MA. Actually, this one should be MAX. Yeah, in the x-axis, we can see that we have this P, okay, going that way at the angle of 30 degrees. Okay, so it is cos, okay, P cos 30 degrees, okay, and then minus, this is your FF, okay, which equal to mu K times N, okay, mu K is 0.25, N is the normal force. Okay, why N is normal force? This one, right? Okay, why it is negative? It is negative because of the direction is to the left, and from here we know that x is to the right is positive. However, this one is to the left, so therefore you will have a negative sign here because the direction is on the opposite direction of your reference axis. Okay, all that, okay, since we only have these two parts here, and that is equal to M. M is given as 80 kg, and we know that in this particular direction, we want this block to move with 2.5 meter per second square, right? Meter per second square. So this is the AX. Okay, this is your AX. And if you solve this, you will get 200 N. Okay. Then we solve for Fy. Okay, why Fy is equal to 0? Okay, why it is equal to 0? Because in the y-axis, you can by logic, this block is already mentioned that it is going to move to the right with this acceleration, okay? And there is no motion in the y-axis, no motion in this y-axis, okay? No movement in that direction. So that's why M A y, because A y no motion in the y direction, and therefore this one equal to 0, and therefore it is equal to 0. Okay, now we look into what are the other forces involved in the y direction. So in the y direction, we can see that we have N, the normal force going up here, and also we have our component going down from this particular P here, okay, and it is sine theta, okay, and then minus, okay, y minus because it is pointing down, okay, y is pointing up is positive, so here P is pointing down, so it is negative. And then we also have this one W, okay, which is 789, okay. How you get this? It is up here, okay, okay. M times A y, or AY is equal to your gravity lah, and it is pointing downward, so it is a negative sign, and everything there is equal to 0. Equal to 0 because no motion in the y direction. Okay. Now we have unknown consist of P and the normal reaction force from this plane, and therefore we can resolve this particular problem, these unknowns. So you have this equation. Let's say this is equation 1, this is your equation number 2. Okay. Then you can solve this equation. For this unknown, you have two unknowns, which is P and N, and then you have two equations. Then you can solve for P, the value of P. Okay, second example here, we have a sample problem where there is two blocks attached and linked together. There are linked here. Okay. Two blocks shown start from rest, the horizontal plane and the pulley are frictionless, so no friction on this part. And the pulley is assumed to be the pulley, the weight of the pulley is not count, especially this one. It's not count in this analysis. Okay, determine the acceleration of each block and the tension in the chord. Chord is this blue color line here. If one call it chord, line or rope, it depends. Okay, now how to resolve this? First, you need to write the kinetic relationship for the dependent motion and acceleration of the block. Write the equation of motion for the block and pulley. Okay, and then combine the kinetics relationship with the equation of motion to solve for the acceleration and chord tension. Okay, this is your reference axis. Okay, don't forget to write this one first. Okay, then as you know that the kinematic relationship is YB is equal to half XA. Why it is like this? Because of YB here, you have YB. Okay, you have 2 YB here, 2 lines, 2 chord support on this one, and you only have 1 line for A. This is your XA. Okay, so therefore you will have this, and the same goes for this part. Okay. Okay, right equation of motion for block and pulley. Okay, we go one by one. First, we look into this particular box A. Okay, for box A, what we have is the normal force, okay, NA, and then we also have the weight of this particle block, WA, and the tension, okay, tension is going that way, T1, okay, and it is the things. So summation of forces is equal to MA times small a with subscript capital A, then T1 is equal to 100 times A. Then for this summation of forces in the y direction, what we have is MB AB. Okay. In the x direction, we only have one forces. Okay, in this case. So that's why we only have this part here. Okay. In the y direction, we look into this. This box here. Okay. So that's why we have MB AB. Okay, MB times G. This one. Okay, this is your weight, weight B. And then minus T2. T2 is here. T2 is, okay, if I zoom on this part, what happened is you have a pulley, okay, and you have something like that, right? Okay, and these particular parts, if you draw from for this particular block B, what happened? You will have this T2. This one is T2. This one is T1. This one is T1. Okay, that is how it works. This is your weight B. Okay, this is similarly what we have down here. Okay, minus T2. Because we define y direction is going down is our positive, therefore going up is negative. That's why minus T2. Okay, it is all depends on your coordinate system. It's up to you to decide. Okay, no problem if you do it the other way around. If you want to do like this, it's also fine. And make sure that during your calculation, everything is consistent, done consistently, and that will avoid any errors. Because the final result will be the same, regardless of your axis system. Okay, now you have this equation. Okay, this is what I have drawn up here, the same thing. Okay, that is equal to 0. Okay, and summation of Fy for this particular point at C of this pulley, it is this the formula that we can derive. Okay, now from all equation that we got, basically we can solve this particular problem. Okay. Okay, we can solve this particular problem. So it is the first part, second part, and the third part for the pulley. Block A, block B, and the pulley at C. So this is all the equation. Okay, just plug in the value, then rearrange the equation, then finally can solve for, in this case, for this T2, which is equal to 1680 Newton. And you can also calculate the acceleration of block A, which is 8.4 meter per second square, and AB is equal to 4.2. What happened is, let's say, at the beginning, you do like this. Instead of you use this coordinate system, you use this one, right? Because sometimes it's big. Sometimes you don't know which one is better. Okay, no problem. What happened is, when, let's say, you use this one, the value that you will get here, AB, you will get it instead of positive, you will get minus 4.20 meter per second square. Okay, if you use this one, you will see that you will get this minus sign, which means that the uh, expression is going downwards. Okay, therefore, like I just said earlier, that this axis system, as long as you do it consistently, you will get the same result. Okay, I mean the direction and the magnitude will be the same. Okay, I think that's all. Thank you.